So again, make sure you take good notes. I did put some new documents up on Blackboard. There's a lot of stuff we got to go through for this topic for this week. This is where I'll introduce what we call circuit theorems. And once we master the circuit theorems, the next thing we'll talk about are methods of analysis. And I think I mentioned to you that as you solve series parallel networks, the circuits become more complicated. And then what we can do is add voltage sources or other type of sources in other places. And at that point, you can't use Ohm's law. You have to use other mathematical techniques to solve the circuits. So that's kind of where we're headed. This topic for today, and actually the rest of this week and some of next week, we'll actually use some of these circuit theorems to help us solve more advanced circuits. So I want you to think about something though. Think about electrical devices. It doesn't matter what kind of device we're talking about. Anything that takes electrical power to operate is an electronic or electrical device. Examples would be a computer is an electrical device, a computer, microwave oven, your cell phone, anything that takes electricity to power it is what we refer to as electrical device. I just call it a device here. Now, what do all electrical devices have in common? Well, one thing they have in common is all electrical devices have at least one input and at least one output. And what do I mean by an input and an output? Well, an input is where you would connect power to any kind of electrical device. So for example, I mentioned your cell phone. Your cell phone has a battery in it, and if you take the battery out, the battery would have tabs in the battery compartment, and when you put the battery in, the battery would attach to those tabs. Those two tabs that make the electrical connection between the battery and the cell phone, those two tabs represent the input of your cell phone. At least one input. It's possible to have more inputs. As a matter of fact, a cell phone actually has several inputs. But I'm referring to where you connect the battery. That's a good way to define the input to an electrical device is wherever you connect power, that's the input. And so I'm showing this, I just call it a device. You can put cell phone here, computer, you can name it whatever you want. We just have a general device, electrical device, and over here is where I would connect the battery. And so I'll call that the input of the circuit, the input of the device. Every electrical device has at least one input. Many have more than one input. Your cell phone has a place to connect the battery. That's an input. But you also speak into the microphone when you talk on the cell phone. The microphone actually produces voltage and current, so that's another input. The antenna is both an input and an output, so it can get complicated, but I want to keep it simple. For us in here, if I have any electrical device, that electrical device will have some kind of input and some kind of output. The input is wherever you connect the battery. The input is wherever you connect the battery. Now, typically in electrical engineering, when we draw these diagrams, and remember the name of an electrical diagram is called a schematic. Electrical engineers call it a schematic. And when engineers draw electrical devices with inputs and outputs, it's customary to put the input on the left side of the device and the output on the right side. So when you see later in the more advanced courses, when you see schematics, let's say for an amplifier or some other device that you maybe designed or you might be troubleshooting, typically the inputs will be on the left and the outputs are on the right. Kind of customary to do that. So notice here for this device, I have two terminals. This is what we call a two-terminal device. I got to have at least two terminals because to power anything is going to take voltage. And you know voltage is two polarities. So I got to have a plus polarity and a minus polarity. So I got two terminals. And any electrical device, when I have a positive place I can connect it and a negative place I can connect it. We call this a two-terminal device. So my input is where I connect the power. And what about over here? Well, the output. Well, the output is going to depend on what the device is. What the output, if I have a motor, the output could be the shaft spinning. So that's a kind of a form of power, but it's not electrical power, is it? Matter of fact, a motor is a transducer that converts electrical energy to mechanical energy. So we put in, on the input side of the motor, we put in electricity, we put in electrical power. What we get out is mechanical power over here. Doesn't really matter though, because any electrical device is going to have an input and an output, but the output kind of depends on the device. If this is a motor, it's mechanical energy over here, horsepower. If this is an amplifier, it's electrical energy over here, but you're going to connect up a speaker to the output so you can get sound. If it's a, I mean, we can go on with examples, but the outputs are just depend on the device. But here's what we can do with the output. Typically, let's take something like, let's use an amplifier. Let's say this is an amplifier. Now, an amplifier is going to have two inputs, right? An amplifier, you have to hook up power to the amplifier. So you have a positive terminal and a negative terminal. If you're installing this in your car, you would hook the positive terminal to the positive terminal on the battery, hook the negative wire here to the negative wire on the battery, and that will power the amplifier. That's one input. But an amplifier also has a second input, because what do you amplify? You amplify sound, so the sound from your radio will run into another input on the amplifier, and so you have two inputs, one for DC power and one for AC sound. And so, as I said, many devices will have more than one input, but we're going to keep it simple. So for us, the input side is going to be where we connect power, in our case, a battery or cell, and the output will be something I hook up to this device to do something. If this device is an amplifier, maybe I hook up a speaker. Speakers make noise, it makes sound. Maybe I hook up a light bulb. Light bulbs light up. Maybe this is whatever this device is, you hook something up and it does something. Well, the thing you hook up to the output, speaker, light bulb, whatever it is, the thing you hook up to the output of electrical device has a name. In general, we call it the load, L-O-D-E. The load. Now that word load can be confusing, because sometimes the word load means the thing you hook up to the device. If this were an amplifier and I'm hooking up a speaker to the output of the amplifier, then the speaker is the load. If this was some circuit that required a light bulb, maybe it powered a light bulb up here, I put a light bulb on the output, then the light bulb is the load. So sometimes this word load refers to the actual thing I'm connecting to the output, but sometimes it refers to the current going to that thing. So they have something called the load and the load current. And sometimes they don't say load current, they say load, but they don't mean the thing you hook up. They mean the current going to that thing you hook up. And what they mean by that is should be evident from the problem statement. Okay, so just realize this has two meanings, but for now, we're going to assume the load is whatever I hook up here. It could be a speaker, it could be a light bulb, it could be anything. So how do I draw a symbol? What one thing does everything have in common? Well, the one thing everything has in common is everything has resistance. So no matter if I'm talking about a speaker, a light bulb, no matter what it is, I can represent any load by resistance because everything has resistance. So typically what we'll do is I will represent any device, anything I hook up to my circuit as a load. So we'll just call this RL, and the L stands for R load. It might be a speaker. If it's an 8 ohm speaker you're hooking up to an amplifier, you show it as an 8 ohm resistor. If it's a light bulb that has a filament resistance of 0.01 ohm, you show it as a resistor, 0.01 ohm. No matter what it is, we can represent that thing as a resistor. So, by definition then, the input of any device is going to be where I connect power, and the output is going to be where I connect the load. Amplifier is where I connect the speaker. If it's your cell phone charger, it's where I connect the cell phone. The output's going to be wherever I connect up the thing that this circuit is designed to power or control. So we have inputs and we have outputs. Now, imagine this is a black box. You can't really see what's inside of it. Everything electrical is really a black box, right? If you hold up your cell phone, you can't see inside of it. It's a black box. But if you were to take the cover off, You see resistors, capacitors, integrated circuits, inductors. You see a lot of stuff you probably don't even recognize yet. You see circuitry in there. Well, I have the same thing here. I got some kind of device. Again, it could be whatever you want. And we know if we were to open it up and look inside of it, there'll be a connection of a bunch of electrical components, different types of components that do different things. Now, since this is circuits 1, and all we've dealt with in this class so far is resistors, then for us, if we open up any electrical device, there are going to be resistors in there. So I could have a really complicated connection of resistors, of circuitry in there. And let's just say we could see inside the box. And let's say when I had it, and I'm going to keep this really simple. I'm going to draw 2 resistors. Any typical device might have hundreds of resistors in it. We're going to keep it simple. So suppose inside of this thing, whatever it is, I have resistors connected up. Maybe I got one like this. I got one like this. Now you probably got capacitors, inductors, IC. You got a lot of stuff inside of the average electrical device. But again, we're going to keep it simple. All we have in our device is these resistors. And maybe this resistor is, let's make this 6 ohms. And let's make this 3 ohms. So if I want to power the device, I'm going to hook up some kind of voltage source to it. So maybe I put my battery over here. So here's my positive terminal. So I take the positive terminal of my battery, hook up right there. My negative, I hook up right there. There is, so again, this might be your cell phone, this might be the charger, or maybe you got it plugged into the wall. This might be an amplifier, maybe this input is a radio, or if it's a DC input, this might be a speaker. Some kind of way you got power going in, you got some kind of energy or useful work coming out, depending on what the device is. And typically, you cannot see inside of the device because they have it in some kind of case or some kind of cover. All, as a human, all you really interact with is the power. Maybe you connect the battery to it, and maybe the load, if you connect speakers up to an amplifier, whatever this load is. But we know there's something inside the device. Now, here's what I want you to understand about this. After today's lecture, you should never look at a circuit the same way again. Typically, when, at least up until this point today, when we talk about like total resistance, or when we talk about total current, we always talk about the total resistance from the point of view of the input. If this battery could see, they had an eyeball and they can see, and I say, all right, student, what's the resistance of this device? Another way to say that is, how much resistance does this battery see? What's the input resistance of the circuit? And you might say, well, you got to hold on a second, because I want to know the resistance inside of this box. I don't want to know nothing about the load resistance. So if I'm going to answer the question, let me be clear on what the question is. If this battery had an eyeball and it can see, if it can see the resistance that it's connected up with, too, if it can see the resistance inside this box, how much resistance will it see? And I'm making the point is that this right here is not part of this. If this is an amplifier, and that 3 ohm resistor and that 6 ohm resistor make up resistance in the amplifier, and this is your speaker, the speaker is not part of the amplifier. The speaker is a device you hook to the output of the amplifier, but it's not part of the amplifier. So if you're going to answer the question, what's the resistance looking in this way? How much resistance does that battery see? The first thing you got to do is remove the load, because it's not part of the circuit. You got to take it off. So now that I've isolated the load from the device, I've taken the speaker off the amplifier, I removed the load from whatever this thing is. Now I can look inside of here and I can see what kind of circuit it is I have. And once I see what kind of circuit it is I have, I can determine the resistance quite easily. See, if I have a series circuit and I ask about resistance, well, that's easy, Because things in series, we just add them up. If I have a parallel circuit, well, that's easy too, because in parallel, we know that we can use the reciprocal formula. I can use the product over sum. If all the resistors are the same, I can use a special case formula we talked about. Point is, we can calculate parallel resistance. So if this battery had an eyeball and a brain, it can think, and wants to see how much resistance is it connected to, what kind of circuit is inside that box right now? What kind of circuit is that?
Series.
It's a series circuit. It is a series circuit. And everybody should see that right now. If you don't let these terminals right here confuse you. A series circuit has one path and one path only for current. And if current is flowing into here, current has only one path to go through. Current's going to go through here, here, and back out. No current goes over here because I've disconnected the load. So wherever current flows is the resistance that this battery feels or sees. And whoever says series, you're right. So here's what I would say. Here's what I would say. The resistance looking into the circuit, into the device, we call that the input resistance. Rn equals 3 ohms plus 6 ohms. My input resistance is 9 ohms. The input resistance of this device is 9 ohms. Now, if I have total resistance of a series circuit, we call that RT. We're doing calculations. If I gave you a series circuit and I said, all right, find the total resistance, you name that RT for R total. If we had a parallel circuit, I said, all right, find the total resistance. We didn't call it the total resistance. Remember I told you we're not gonna call it RT if it's in parallel. We're gonna instead call it REQ, or equivalent. It's still a total though. So if I have resistors in parallel, I call it REQ. I know how to get that. Either way, whether I talk about RT or REQ, is only in textbooks. It's only in textbooks. What am I talking about? Well, there's the textbook world, and then there's the real world that you guys will experience when you graduate from here and go get a real job based on your degree. If you work in the electrical world, you will never ever hear them talk about total resistance. You will never ever go to Procter & Gamble, GE, none of those technical places and hear them talk about the total resistance or equivalent resistance. You will hear the engineers say, people are actually doing this stuff, not just reading the textbook, they'll talk about the input resistance. The input resistance for them is what we call total resistance or REQ for us. So in the theoretical world, in the textbook world, it's REQ and RT. When you get out in the real world, it's the input resistance. But here's the point of this lecture. Here's the important thing. Up till right now, if I say find the total resistance of the circuit, you'll do what you just did, and you'll say, well, that's a series circuit. I add them up, I get 9. And you would be correct. But every circuit has a point of view for not only the input, but also for the output. Every circuit has a point of view, not just for the input, but also for the output. So what I'm saying is, yes, from the point of view of the battery, if it had an eyeball, it would see 9 ohms. That's old stuff. That's RT, that's REQ. But now I'm saying, here's the new stuff. Not only does this have a point of view for resistance, this does too. The load actually sees a certain amount of resistance also. So I can ask the same question. If this had an eyeball and can see how much resistance it's connected to, it's connected to 3 plus 6, they're a series, that's 9. I can ask the same question about this load resistor. If it had an eyeball and it's looking back this way, how much resistance does it see? And logic would suggest if the resistance looking in this way, if that's the input resistance, then the resistance looking in this way, we call that the output resistance. Every circuit not only has an input resistance, every circuit has an output resistance. And that's what I want to talk about today. how much resistance will this thing save looking back this way, looking into the other end of the circuit. And you'll see why that's really important. Turns out to be really important. Now, we got a problem. The problem is that if I want to measure resistance, and I take my ohm meter and I put it right here. See, I take my ohm meter and I put it right here. Get my digital multimeter, I change it to ohms. I got that circuit exactly. Let's make this 9 volts. Let's make it 9 volts. Now I say, all right, I want you to measure the output resistance. You say, all right, Singleton, I can do that. So you take your digital multimeter, you put it on ohms, you connect it up right here. You won't get a correct reading. Why would you not get a correct reading if I connect it up? What's wrong with just connecting it up to the circuit as you see it right now? Why won't I get a correct reading?
Is it because the current's going to follow the series circuit around and not come out to the end?
Good guess, but that's not it.
Okay.
Anybody
You're
else?
making a short.
Say it again.
You're making a short with the ohm meter.
Ohm meters don't make a short, and I don't know if I talked about that. We need to talk about ohm meters. Don't a voltmeter and an ohm meter are open circuits. The amp meters are short, so no, that's not it either. What's wrong with connecting up as you see it? What's wrong with connecting up my ohm meter right here with everything you see in the circuit? There's one thing I need to do if I want to measure resistance. What do I need to do? Well, the problem is right here. You can't measure the resistance of anything with the power hooked up. If you don't believe me, when you come in the lab on Tuesday, wire something like this up, turn your power supply on or whatever you want, and then try to measure the resistance of the resistor while it's connected up to power. It won't work. You can't do it. So if you want to measure the resistance looking in this way, the first thing you got to do is you have to set the voltage source to 0. You have to set the voltage source to 0. How you set the voltage source to 0? I don't mean come in here and turn the knob down. That's not what I'm saying. The way you make a volt, let me show you. All right. Say I had this. Say I have a battery. And I got 2 equal resistors. And this is 10 volts. If I got 2 equal resistors, this is R and this is R. I got 2 equal resistors. And how much voltage would each resistor drop? If I have 2 equal resistors in series, each one would drop what?
Half.
Each one's going to drop half, 5 volts, right? 5 volts. So if I take my meter and put it across here, it's going to read 5 volts. Put it across here, it's going to read 5 volts. I put it from here to here, it's going to read the whole 10. Because 5 plus 5 is 10. So I'm going to hook my meter up right now. Watch me do this. I'm going to hook my meter up right here and here, and it's going to read 5 volts. While the meter's hooked up, I take a piece of wire. Now remember, this piece of wire is short and 0 resistance. While the meter's hooked up, you're looking at the meter, you're reading it, and while it's hooked up, somebody comes in here and does this. They connect that piece of wire, that short circuit between this point and this point. What would the meter value change to?
0 volt.
0 volts. 0 because you shorted out the resistor. The point I'm making is the way you set a voltage to 0 is by shorting it out. You place it with the short circuit. So if I want to measure the ohm meter here, how many ohms does the output see? The first thing I got to do is take the battery and set it to 0. And the way you set a voltage source to 0 is by replacing it with the short circuit. So I'm going to come over here and remove the battery. And I'm going to replace the battery with a short. I'm going to short it out. And now the voltage is 0. You set a voltage source to 0 by replacing it with a short circuit. Now when I try to measure over here with my ohm meter, I can get a reading. This battery is not going to interfere with my reading. How much will I read? What kind of circuit is it looking this way?
A parallel circuit?
A parallel circuit. Now, let me pause, because some of you right now in your mind, when I said that, you say, well, that's a series circuit. It is not a series circuit. It's a series circuit looking this way. Remember, a series circuit has what? A series circuit has only one path through which current can flow. If current went this way, the only way current can get into the box and out is to go through here, here, and back out. One path for current. These two are in series, therefore the total resistance is 3 plus 6. If I sent current the other way, if current flowed this way, at that node right there, some current would go that way, and some would flow all the way around this way. So they couldn't be series, has to be parallel. Well, what's the value then? Well, I have, looking in this way, I have 3 ohms in parallel with 6 ohms. If you can't see that that's in parallel, let me redraw it for you. What you have is that 3 ohm like this. You have these 2 terminals like this. You have that 6 ohm like this. And then because you replaced the voltage source with a short circuit, because you connected the short between here and here, you connected the bottom of that 3 ohm to the bottom of the 6. If I move the 3 over here, what you would have is this and that. Clearly, these resistors are in parallel, not series. So, looking in this way, look. Looking in this way, I see 3 plus 6. This battery thinks it's hooked to 9 ohms. But looking in this way, I see 3 in parallel with 6, which if you do the math is 2. The input resistance, looking this way, is 9 ohms. The output resistance, looking this way, is 2 ohms. Same circuit, different points of view. The battery thinks it's up to one amount of resistance, the load sees something else. Input resistance, output resistance. The input resistance is what you talk about in the real world. In the textbook, then they'll call it RT for R total, or REQ for R equivalent. The output resistance is what engineers talk about in the real world. When they talk about the resistance from the point of view of the load, they call it the output resistance. In here, in theory, in textbooks, we don't call it the output resistance. We call it the Thevenin resistance. The Thevenin resistance. It's a big word, it's a different word, but all it means is the resistance looking from the point of view of the output device. The Thevenin resistance is the output resistance. Now, questions over what I just talked about? All right, I want to show you something. So if you didn't print the documents out, if you got your documents, look at your documents. If you did, I'm about to share something with you. Oh, did I not upload the files? Okay, I'm about to share something with you on the screen. So have a look at your screen. Now read Roman numeral 1 to yourself. Read Roman numeral 1 to yourself. Now let me read it to you. Number 1, it says, Thevenin's theorem. Any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Thevenin's theorem. Any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Wow. What the heck does that mean? Well, let's break it down. Let's break it down word for word. Definitizing theorem. Any, look at this right here. Two-terminal. What does that mean? What does that mean, a two-terminal? Two-terminal network. What does that mean?
That it has
Electric
positive and negative.
device.
I think you guys said the right thing, but you were talking together. It has what?
Yeah, go ahead.
Go ahead.
Well, he said positive, negative, and I said it's an electric
Exactly.
device. Yeah.
And that's all it means. Every electrical device is a two-terminal device. Why? Because voltage requires a positive terminal, voltage requires a negative terminal. So we're talking about two terminals, positive and negative. That's all that means. Any two-terminal, positive and negative, any two-terminal linear. Linear. What's that mean? Linear. You know what it means. What does linear mean?
Side by side.
What
Or-
does it mean mathematically? If something is linear, if I made a graph of it, what would that graph look like?
Straight line.
A line. Yeah, a line. Now, let me take this off and go back to the camera. If you graph this right here, I tell you y equals 2x plus 1. If you graph that, do you know you'll get a line? Do you recognize that as a line? And you should, I can't see you, I can only see 3 people right now, but the other 12 of you who too scared, that's a line, right? That's a linear equation. If I graph this, or if I graph this, will either one of the second two give me a line? Well, if you don't know, the answer is no. If I graph this, I will not get a line. If I graph this, I will not get a line. If I graph this, I'll get a line. How do I know? Because all you got to do is look at the x. If x is raised to the first power, then when you graph it, you'll get a line. If it's the second power, third, or some other power, you won't get a line. It's nonlinear. Nonlinear. So if I can express it, the variable to the first power, then I get a line. That's all this means right here. Let's go back to my sheet. Any two-terminal, positive and negative terminal. Linear. Linear means that if you wrote an equation for it, the variable is to the first power. For instance, voltage equals I times R. Both I and R to the first power, voltage is linear. Current is V over R. Both the V and the R are to the first power, current is linear. If a quantity can be represented by a linear equation, then we say that that's a linear quantity. Any two-terminal, positive and negative, linear, I can write an equation for it, and if I graph the equation, I get a straight line, just like you did in that lab, the Ohm's Law lab. You graphed the current voltage relationship, you did it 3 times for 3 resistors, you got 3 different lines. We deal with linear devices. We do have some devices in electrical engineering that are non-linear devices, but most devices we deal with, I shouldn't say most, many devices we deal with are linear devices. So this, what we're talking about right now, works for linear devices, linear circuits. So, any two-terminal, positive and negative, linear, I can model it with an equation where if I graph it, I get a straight line. Bilateral. What does bi mean? Bilateral. Bi means what?
2.
Two.
Two, right? let me show you what we mean when we say bilateral. I'm going back to the camera. A resistor is a bilateral device. Why? Well, if I have a resistor and I hook up a battery to it, and current will flow like this, that direction. If I flip the battery over, current will flow in the other direction. So a resistor is a bilateral device, because current can flow both ways through a resistor. The average light bulb is a bilateral device, because if I put the battery to it one way, current will flow one way. If I turn the battery over, current can go the other way. It's a bilateral device. Anybody ever heard of a diode? What's a diode? You ever heard of that?
So on the diode, the current flow just on the one way.
A diode only allows current to flow one direction. It is not a bilateral device. With a diode, and I'll just show you the symbol for it. Now, if you're electrical, you'll get the diodes when you take electronics. You'll get to this later on. I'm just showing you how it works. The symbol for a resistor is like this. The symbol for a diode is like this. If I hook up a battery one way in the diode, then current will flow through the circuit. If I flip the battery over, the diode would not let the current go the other way. Diodes only allow current to go one direction and not the other. So a diode is not a bilateral device. Most devices, many devices are bilateral. So what I'm reading right now only works for bilateral devices or bilateral circuits, a circuit through which current can flow both ways. If I reverse the battery, current can flow in both directions. So any two-terminal, positive and negative terminal, linear, I can write an equation for whatever quantity I'm talking about, and every equation, every variable in the equation is to the first power, which means if I graph it, I get a line. Bilateral, current can flow both ways through the device or through the circuit. DC, well, we all know what that means, direct current. Any two-terminal linear bilateral DC network can be replaced by what? Can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Now let me explain what this is saying. Practically every circuit that you're going to deal with is going to be a linear, it's not necessarily DC, but it's going to be linear and bilateral. So pretty much everything you come across is going to be that. It says that basically in a nutshell, Thevenin's theorem, and by the way, Thevenin was a person who came up with this theorem. That's why it's Thevenin apostrophe S is his theorem. The apostrophe shows that he possesses a theorem. So it's named after him. So Thevenin realized that I can take any circuit. I don't care if that circuit has 1,000 resistors in it and 50 voltage sources. I don't care how many components it has in it. You can take it and you can replace it with the equivalent circuit consisting of one voltage source and one series resistor. Let me draw it for you. The equivalent circuit that Thevenin was referring to was this. What Thevenin was saying was you can have a complex circuit, any number of resistors, any number of voltage sources. As long as it's a linear bilateral DC network, you can replace that complicated circuit with this circuit, and this circuit will be an equivalent circuit to the one you replaced. What is an equivalent circuit? Well, when I say equivalent circuit, what do I mean? Equivalent from the point of view of the voltage source. Say over here I had a complicated series parallel circuit, all kind of stuff inside of it, but I got one battery on it. If it's an equivalent circuit, I can take the battery from the original circuit and move it over to the equivalent, not the battery, but the load, I'm sorry. It's equivalent from the point of view of the load. If I have an equivalent circuit, I can take the load and move it from the original circuit and put it over here on this circuit, and it can't tell which circuit it's hooked to. It's equivalent. And you can see, hopefully you can see the power in this. Because if I can take any complicated circuit, no matter how many resistors, how many voltage sources are in it, if I can reduce it down to this, which one would you rather do the analysis on? The circuit over there with 1,000 resistors and 50 voltage sources, or that? Most people will want to do the analysis on this, because this simple circuit behaves exactly like the complicated circuit. This simple circuit is called the Thevenin equivalent circuit. Write that down. The Thevenin equivalent circuit. And the Thevenin equivalent circuit is the circuit that any output device sees when hooked up to a device. The Thevenin equivalent circuit, I'm going to say that slowly. The Thevenin equivalent circuit is the circuit that any output device sees, speaker, light bulb, whatever the output device is. It's the circuit that any output device sees when you hook it up to the original circuit. This resistor right here is called the Thevenin equivalent resistance, or RTH. And this voltage right here is the Thevenin equivalent voltage, or VTH. So anytime you want to see what kind of circuit an output device is looking at, if you want to know what does the original circuit look like from the point of view of the load, what you want to do is Thevenize the circuit. When I say Thevenize the circuit, you want to go from the original circuit to that. So the question becomes how you do that. How you go from the original circuit to the Thevenin equivalent circuit. And that's what I want to give you the steps to doing that right now. So get a sheet of paper, because I'm going to list some stuff out and write it down. Now this is in your book, but it may not be in this order. So if you're just looking at me and you're not writing anything down, well then I'm not going to say you'll be lost. You're going to have a harder time. So please write these steps down. What I want to do is 10 till 2 right now. I want to give you the steps, and in the last 5 minutes, I might go over a little bit. To really understand it, I got to show you an example, a really simple example. So I'm going to give you the steps, and then I'm going to give steps a second time using examples. That's why on this sheet right here, see, if you were here on campus, and I would actually pass this out to you, this right here. See how much space I left down here? Because what I want you to do is draw these examples I'm about to go over right now. You would do that in class. So less space there for you. But since you're not here in class, I got to trust you at home to go ahead and copy this stuff down. So I'm going to give you some steps to write down. Step number 1. Well, here's what we're doing. Here's what you want to title it. These are the proper steps to Thevenizing a circuit. I'm giving you the steps to Thevenizing a circuit. Now, what do I mean by Thevenizing a circuit? To turn the circuit into the circuit that the output device sees when looking back into the circuit. Step number 1, remove the load. Step number 1, remove the load. Remove the load. And we represent the node with the resistor, so you can say low resistor if you want. But step 1, remove the load. Step 2, name the terminals. Name. I'm saying name. Name the output terminals. Usually call one A and B or something like that. So step 1, remove the load. Step 2, remove, step one, remove the load. Step two, name your output terminals. Call one terminal A and one terminal B. Step three, you want to find the voltage. You want to find the open terminal voltage on the output of the circuit. Find the open terminal voltage on the output of the circuit. And all that means, open terminal voltage, all that means is you remove the load, which you've done that in the step before. So find the open terminal voltage. Now make sure you're writing these down because we're about to do an example, and I want you guys to read this back to me.
Can you repeat the last one? It's find open terminal voltage.
Yeah, and the open terminal voltage is the voltage measured at the output terminal with the load removed. It's the voltage measured at the output terminals with the load removed. The value you get for the open terminal voltage is the value for VTH. The value you get for the open terminal voltage, that's your VTH. Step four, set the power source to 0. Now, step 4 is going to have an A and B. So write step 4, and for step 4, I want you to write this down. Step 4, set your power source to 0. Step 4, set your power source to 0. Right up under that, step 4, set your power source to 0. I want you to write A. So it's a 4A and a 4B. Step 4 should be set your power source to 0. And then right under that, A. If you have a voltage source, you set a voltage source to 0 by replacing it with a short circuit. Set a voltage source to 0 by replacing it with a short circuit. Set a voltage source to 0 by replacing it with a short circuit. Set a voltage source to 0 by replacing it with a short circuit. And then there's a B. 4B, set a current source to 0. Current. Set a current source to 0 by replacing it with an open circuit. Set a current source to 0 by replacing it with an open circuit. Set a current source to 0 by replacing it with an open circuit. And the last step, step number 5, is look into the output terminals and determine the resistance. Step 5. Look into the output terminals, determine the resistance. That value will be your Thevenin resistance, RTH. Look into the output terminals, determine the resistance, and that value will be your output resistance, your Thevenin resistance, RTH. Now, if you missed a step, that's okay, because we're going to go through it one more time. I got like 5 minutes. I'm going to go through it one more time, but this time I want to go through, and I want you to draw what I'm drawing on the board. We're going to go through step by step, and for each step, you should have a picture. You should have a picture, and you got the step already. You know what's going to happen, but I want you to draw a picture so you'll see what each step looks like. That's why I left all that space on that handout. So if you actually do what I'm saying, then everything else we'll do on Friday will be way easier. Okay, so let me make up a circuit real quick. Real simple circuit. So let's say I got this. Now, I want to add another resistor, but I want it to be my load resistor. So to show that it's the load resistor, not part of the circuit, here's what I'm going to do. These are like connection points. Those are what we call the terminals. I'm going to show the resistor connected with like this. I'll call that RL. That's how I know this is my load resistor. And let's say that I got R1, R2. Let's make this 3 ohms, 6 ohms, 9 volts. But here's my circuit. Now what I want to do is I want to Thevenize the circuit. I want to turn this circuit into this circuit. The Thevenin equivalent circuit is the circuit that this load sees. This load thinks it's hooked to this and not that. So how do I go from this circuit to this circuit? Well, let's go back over your list. What's step 1 say? Step 1 is what?
Remove the load.
Remove the load. So on your paper, and I'm going to go slow. I'll probably go past 2 o'clock. But on the paper, you go, for step 1, I want you to draw this circuit with the load removed. Remove the load. Draw this circuit and write step 1. I'll wait. I got plenty of patience. Draw that circuit, step 1. Remove the load. You're going to draw this circuit 5 times because we got 5 steps. So step 1, remove the load. That's what it looks like. And you don't have to draw a Picasso, you know what I'm saying? Just sketch it real quick and we'll move on. But, you know, make it neat enough where you can go back and read it. So step 1, if you apply step 1, this is what your circuit should look like. Step 1, remove the load. Step 2 is what?
Name terminals.
Name the terminal. Call one terminal A. Call the other one terminal B. So redraw this for step 2 and just put an A and a B there. And while you're doing that, let me tell you why we do this. As you'll see, and you might have already seen, when you have a complicated circuit, sometimes to solve it, to make it easier to solve, you got to redraw the circuit. We did that before. Remember we did that? We kept drawing the circuits over and over again until we got down to a series circuit. Well, when you name the terminals, when they move around, when you redraw it, you can keep track of them better. The only purpose to naming the terminals is so you can refer to them and keep track of them as they move around if you have to redraw the circuit. So, step 2, name the terminals, call one terminal A, one terminal B. Doesn't matter which one you call A and B, just name them. And what's step 3?
Find the open terminal voltage on the output of the circuit.
Okay, so find the open terminal voltage. Here's the output of the circuit, and those terminals are open. What do you mean they're open? Because it had a resistor on it. Now the terminals are not open because I put the resistor back. Open terminal means you're taking the resistor off of those terminals. So I open them. These terminals are now open. Find the open terminal voltage between A and B. If you had your voltmeter, you connect one to terminal A and one to terminal B, you'll be measuring the open terminal voltage. The open terminal voltage would be whatever voltage you're measuring from terminal A and B with no resistor, with the low resistor gone. It's not connected between A and B anymore. If I connect, now look at this. If I connect my meter between A and B, which resistor am I across? Am I across R1 or R2?
R2.
Would be R. I was gonna say
R2. I'm across R2. If I connect a terminal from my meter here and here, I'm across R2. What that means is whatever the voltage drop is across R2 is the voltage I will measure from A to B. Because point A is connected to the top of R2 and point B is connected to the bottom of R2. So whatever I'm measuring from A to B it's going to be the voltage drop across R2. If you find the voltage drop across R2, then you found the voltage from A to B, and that voltage from A to B is what we call the Thevenin voltage. So let's do that. Let's find the voltage from A to B. Well, there's two ways to do it. I'm going to show you both ways. Now, guys, I'm going to go over by about 5 minutes, so if anybody has to take off, go ahead and sign out, but please come back and watch the rest of this video. Because when we come back on Friday, I'm going to assume you know these steps. We're just going to start doing examples, and you're going to be confused if you don't watch this video. So please come back and watch the end of the last of the video. So, now this is a series circuit, and anybody can solve a series circuit. There's only 3 steps to solve a series circuit if you know all the values. Step 1, you're going to find the total resistance. Step 2, you're going to use that to find the total current. And step 3, you'll find your voltage drop by using Ohm's law. So, step 1, looking this way, what's my total resistance in the circuit?
9.
9.
9 ohms. 9 ohms. Now I can use that in Ohm's law to find the current. I got 9 volts on 9 ohms. I got 1 amp. So I got 1 amp flowing in this circuit like that. And then I want to know the voltage drop across the 6 ohm resistor. Well, that's easy now. The voltage across 6 ohm resistor, V2, is going to equal the current through the 6 ohm times the value of the 6 ohm, 6 volts. 6 volts. What does that mean? Well, what it means is, it means the voltage from A to B is 6 volts. That means VTH is 6 volts. Whatever that open terminal voltage is your Thevenin voltage. Now I told you I'm going to tell you 2 ways to do this. Another way to do this is called the voltage divider rule. Voltage divider rule. You abbreviate that VDR, voltage divider rule. And I like to use a voltage divider rule. I mean, you can do it this way, but I use a voltage divider rule. It's just a little bit quicker. Let me show you what it looks like. The voltage divider rule says that if I want to know the voltage drop across a resistor, I take that resistor, divide by the total resistance. Take the resistor I want to know the voltage across, divide by the total resistance, and multiply that fraction by the total voltage. That'll give me, let's call this R2. That'll give me the voltage across the resistor I want to know about. So, I know the voltage drop is 6. Using Ohm's law in this method, I know it's 6. If I want to do the same thing using the voltage divider rule, I would have been like, all right, what resistor do I want to know the voltage across? I want to know the voltage across the 6 ohm. Put that in the numerator. Divided by the total resistance. Well, you told me the total resistance was 9. This is that. Multiply that fraction by the total voltage. Well, the total voltage is 9 volts. I do the math here, I see that this 9 and that 9 cancel out, and so my answer is 6 volts, which is what we got right there. The reason I like doing the voltage divider rule is it's the same as this, but I never have to find the current. I go right from here to the answer. So as we go through this Thevenin stuff, I'll use this a lot, voltage divider rule. So look it up in your book, look it up on YouTube, look it up, know how to use it. If you don't want to use it, you can always use Ohm's law, but you'll see me using VDR, voltage divider rule. Either way you look at it, we got 6-point answer. Now what does that mean? Well, that means in the Thevenin circuit, in the equivalent circuit, This is VTH. And we got 6 volts for that. The Thevenin equivalent voltage is 6 volts. Whatever your open terminal voltage is in the original circuit becomes your Thevenin equivalent circuit in the equivalent circuit. Thevenin voltage in the equivalent circuit. Now we got one more thing to do and then we're finished. I found VTH, the Thevenin voltage. Now I got to find RTH, the Thevenin resistance. What's the next step?
Set the power source to 0 volt or 0.
Set the power source to 0. So the first thing you got to do is determine what kind of power source you have. You just look at it. Well, that's a voltage source. You set a voltage source to 0 by replacing it with a short circuit. We ain't really talked about a lot of current sources yet. We'll talk about it. But if that were a current source looks like this. So you've seen that symbol in your book, that's a current source. If I had one of these in there for power, then I would replace that with an open circuit. You set a voltage source to 0 by replacing it with a short circuit. You set a current source to 0 by replacing it with an open circuit. So I got to set the voltage source to 0. So let me do that. We'll take it out, and I'm going to short it out like this. So draw that picture on your paper. That's step 4. You set the power source to 0. And the last and final step will be what?
Look into output terminals, determine the resistance.
All right. So here's your eyeball. Here's your eyeball looking into the output terminal. What kind of connection do you see between those two resistors? How are they connected to each other?
Parallel.
They're parallel. If you move this resistor over here, you'll see that the 3 ohm is like that, and connected to it is the 6 ohm, and then you have terminal A and terminal B. At the angle, it's a little hard to see, but if you move it to the side, you can see they got to be in parallel. Another way is the current will move in this way, some will go that way, and some will go that way. If there's 2 paths for current, they can't be series, it's got to be parallel. Either way you look at it, the total resistance is going to be, RTH, going to be 6 in parallel with 3. Well, you can use 1 over R rule, you can use product over some, whatever you want. If we use REQ, is R1, R2 over R1 plus R2. This becomes 6 times 3 over 6 plus 3. I got 18 over 9, which is 2. My equivalent resistance is 2. That means my Thevenin resistance, RTH, is 2 ohms. This is the Thevenin equivalent circuit. Now, all right, big deal. What does that mean? Here's what it means. If I put the load resistor back on this circuit, so that's the speaker, the light, whatever it is the load. If I put it back on the original circuit, if I took it off of here and moved it over here, that resistor could not tell which circuit it's hooked to. In other words, this load resistor, it doesn't know anything about a 9-volt battery and a 3 ohm resistor and a 6 ohm resistor in parallel. It knows nothing about that. What it sees is this. It sees only 6 volts and 2 ohms of opposition. it sees something totally different than the source. Remember, the source is on 9 ohms. Resistance looking this way, it thinks it's hooked to a 9 ohm resistor. Well, this thing right here thinks it's hooked to a 2 ohm resistor and a voltage source of 6 volts. The output quantities and the input quantities are totally different for any circuit. Now, there's one more thing I need to talk about, but I think I'm out of time, so I'm going to say this on Friday. One reason we want to be able to do this is because if I have to do an analysis, it's way easier to do an analysis on this than on this one. I can do either one. If this circuit is equivalent to this, then whatever I would do to this one would affect this one the same way because they're equivalent. I would rather work with the simple circuit. So one reason we Thevenize is because the Thevenin circuit is simpler. It's easier to work with. The second reason we Thevenize, and I'll say it, but we'll talk about it on Friday, is something called maximum power transfer. Maximum power transfer. So in order to talk about this, I can only talk about it in relation to the Thevenin circuit. So I'll explain that on Friday, and then this is a whole other theorem. I can't talk about this if you don't understand how to Thevenize. So we'll talk about that on Friday. Well, guys, thanks for hanging in there with me. I'm almost 15 minutes over. We'll do this again, and this is our first look at this. It's all new stuff. I got plenty of practice problems for you to do, so we'll do more of this stuff on Friday. Anybody have any quick questions for me before we sign off?
So I just want to make sure that when you took that first circuit that you drew,
Yeah.
and you took the what was that first step? You took the load off. You removed the load.
Remove the load.
So then you drew your Thevenin's current circuit.
Yep. Didn't have this load on it.
Right. So basically you just had, so when you took the load off, you took the, what was it, R4 and R6 off. And so you were just looking at the R1 and R2, correct?
Well, there was no, what do you mean R, you said R4 and R6? There was no R4 and R6.
Okay.
What I had was, I had this and I had, just had that load resistor there. So to start this, all I did was, the first step is to remove the load. So I took that off.
Right.
Because it's not part of the original circuit. The speaker is not part of the amplifier. It's two different things, so I took it off.
Okay.
That's the first thing I did. And then we followed those steps. Next step would be to name the terminals, A and B.
Yep.
And then once you get to that, once you remove the load, you ask yourself this question. If I took my voltmeter and put across those terminals,
Right.
what voltage drop will I measure? It turned out we measured voltage drop across the 6.
Right.
Because of what the circuit is, but you want to ask yourself that same question. If you measure from A to B, what voltage would you measure? And the answer to that is just look to see what resistor you're connecting across.
Okay.
Now we'll do more of this. I mean, I don't expect you to get it. You know, you guys, we got to practice this. This is the part of the course where students start to have a little problem. So I understand it's new, but we'll do enough of this to where you'll get familiar with it. I have to be honest and say though, if you can't do series parallel analysis, then you're gonna have trouble doing this. So you want to keep practicing your series parallel stuff. Get good at that. It'll make this way easier. Okay, so you got to keep practicing that.
Okay.
Guys, I'll see you on Friday. Have a good rest of the day.
You too.
See you Friday.